Hello and welcome to our Calculus 1 final exam review. In this video, we're going to be going through all of the problems on the practice final exam for this course. Let's get started. Problem number 1. They want us to evaluate the limit using limit laws or facts. If an answer does not exist, we're going to write DNE. And our first limit says we have the limit as x approaches 2/3 of this rational expression. This can be done with evaluation, simply plugging in the 2/3 for all of the x's if we do not get an error or an undefined situation. So I plugged this expression into my Casio ClassWiz. You can see that I can plug it in exactly the way that it looks with all the fractions. And when I hit equals, I get an error, which indicates that the denominator is 0. We're having a divide by 0 error. And so in order to figure this out, to calculate the limit, we're going to have to do some algebraic manipulation. So let's blow this up and make it a little bit bigger, easier to see. What we notice in the numerator is that we do have the difference of squares. So we're going to try factoring the numerator. That's going to give us 3x plus 2 and 3x minus 2. And in the denominator, we have a trinomial with a lead coefficient. And the technique that I teach my students how to factor those is the 3R method. So the way that that works, we're going to take the 18 and remove it, and instead multiply by the 10 at the back. That'll give us x squared plus 3x minus 180, and then we can try to factor this standard trinomial. We're going to have x and x. The signs are going to be different, and after a little bit of looking, we find that that is 15 and 12. 15 minus 12 is positive 3. 15 times negative 12 is negative 180. Now the second R, remember first we remove the 18, then we need to replace the 18 in front of each x, and the third R is reduce. 18 and 15 reduced by 3, 18 and 12 reduced by 6, and that's going to give us 6x plus 5, and on the other one we're going to have 3x minus 2. And so that's how this trinomial is going to factor. 6x plus 5, 3x minus 2. Now we can see that we do have a common factor that we can eliminate, and that's going to simplify the rational expression to 3x plus 2 over 6x plus 5. And now that we have that simplified, we're going to see if evaluation will work. And evaluating with our Casio ClassWiz, we can see that that will work out to be 4/9, and that is going to be the answer to this problem. So, making it official, we would say the limit as x approaches 2/3 of 3x plus 2 over 6x plus 5 is 4/9, and that's going to do it for the first problem. Problem number 2, we have the limit here as x approaches infinity, again of a rational expression. One of the most effective techniques here is to divide top and bottom by the highest power of x. And so what I'm going to do is I'm going to divide top and bottom by x squared, since that is the highest degree of the variable. And that's going to give us 9x squared over x squared will simplify to just 9, minus 4 divided by x squared is going to stay a fraction. In the denominator, 18x squared divided by x squared is just 18. Plus 3x over x squared would be 3 over x reduced, minus 10 over x squared stays a fraction, And now what we can do is we can say, okay, what's going to happen if x gets infinitely large? Well, these fractions, if x gets infinitely large, a fraction itself gets infinitely small if the denominator gets infinitely large, but the numerator doesn't change. So all three of these fractions are effectively going to go to 0, which will leave us only the 9/18. And so we can say that this answer is going to be a half. And that's it for problem number 2. Next, number 3, we have the definition of derivative. We want to find the limit as h goes to 0 of the difference quotient given this function. And the first step is to replace every x in f of x with x plus h. So that'll give us x plus h quantity squared minus 1. Next, we need to subtract the original function, which is just x squared minus 1. And that is all divided by h. And don't forget that we need to write the limit as h goes to 0 every step until we can let h go to 0. And no, it's not now, because if I let h go to 0, the denominator would be 0, and that's undefined. So here we go. Next step, we're going to have the limit as h approaches 0, and we need to do the FOIL method here. So foiling x plus h is going to give us x squared plus 2xh plus h squared minus 1, and then this minus needs to distribute all over h. Now notice in the numerator that x squareds will cancel and the 1's will cancel. And if you notice, all of the remaining terms in the numerator have an h. So now we're going to say the limit as h approaches 0, factoring out the h, will give us 2x plus h all over h. And now these h's will reduce out. So now what we can do is we can say, okay, now we can let h go to 0 since we don't have the divide by 0 problem, meaning that this guy's going to go to 0, and the answer is simply going to be 2x. And that's going to do it for this problem. Next, given that f of x is the square root of x, we need to use the definition of derivative to find f prime of 2. So this time we're going to use the definition of derivative that says the limit as x approaches our value, which in this case is 2. If you remember, the formula for that said the limit as x approaches a, and a was the number we're concerned with. So we're going to say the limit as x approaches 2 of f of x minus f of a all over x minus a. That was the formula. Now let's go through and replace the pieces with what we've got. F of x is the square root of x. F of a, where our a is 2, would simply be the square root of 2. And then in the denominator, a again is 2. So this is our limit. We're looking for the limit as x approaches 2. And we could do direct substitution if we didn't get a divide by 0 error. And so here, again, we're going to have to do some algebraic manipulation so that we can let x go to 2. So what we're going to do is we're going to take the numerator and the denominator, and we're going to multiply by 1. Okay, not really, but yes, really, 1. Meaning that we're going to multiply by something over itself, which is effectively 1, and our goal is to get rid of the radicals in the numerator. So to do that, we want to multiply by the conjugate. That is the same radical stuff with the opposite sign. We have to do that to top and bottom, and then we're going to get to do the FOIL method. Okay, here we go. Square root of x times square root of x would be the square root of x squared, which is just x. On the outside, we get a positive square root of 2x. On the inside, we get a negative square root of 2x. Notice that those terms are equal but opposite. They will cancel. And last, negative square root of 2 times square root of 2. We have a negative times a positive, which gives us a negative. Square root of 2 times square root of 2 is square root of 4, which is 2. I'm going to leave this factored. X minus 2 times square root of x plus square root of 2. I don't recommend that you FOIL the denominator. And here's why. If we simplify, having the limit as x approaches 2, now the numerator is simply x minus 2. And the denominator, do you see it has a common factor with the numerator? And so what we're going to be able to do here is reduce the fraction. The x minus 2's will divide out and make 1. Really, there's a 1 up top. And then at this point, we should be able to let x go to 2 right here. And so that would give us 1 over square root of 2 plus square root of 2. Those are like terms. So we can add those and get 2 square root of 2. And there's our answer for that problem. Next, number 5, it says, how would you define f of 0 to make f continuous at 0? And this means we have to know what it means to be continuous. Remember, there were 3 conditions that had to be met. The limit as x approaches a, in this case 0, of the function has to exist. F of 0 has to exist. And the third step was that the limit has to equal the function value. And so where this fails in the continuity is that f of 0 does not exist. If you try to evaluate at 0, you're going to get a divide by 0 error. And so the function is actually undefined at 0. And so then what we're going to do is we're going to try to figure out what we would let f of 0 be so that it is continuous. Well, looking over here at our criteria, we know that the limit as x approaches 0 has to equal f of 0. So we need to know what the limit is, or if it exists at all. That would definitely be a criteria that has to be met. And once we know if it exists and what it is, then we will know what to set f of 0 to be. Now, to find the limit of this function, we're going to set this up. The limit as x approaches 0, negative 2 sine of 2x over x. If you're not exactly sure how to maybe approach this, algebraic manipulation or other techniques to avoid the divide by 0 error, your fallback method, your safety net, so to say, is to make a table. So what I'm going to do is I'm going to make a table of values that approach 0 from the left and right. And then I'm going to see if I can determine what the limit is as we get closer to 0. So let's do about 3 numbers. I think that's the way we normally did it in class. From the left, negative 0.01, and from the right, 0.01, and then make those get a little bit bigger. Maybe negative 0.1. Maybe negative 0.5, and then those need to be symmetric. So over here, this would be 0.1, 0.5. And then all we have to do is evaluate the fraction for these predetermined values and see what the y values are. So just a reminder that when you're calculating with your scientific calculator here, you do need to be in radian mode. Notice on my ClassWiz, I am able to input that just the way it looks. Here I've replaced the x's with negative 0.5, and we're going to get negative 3.366 rounded. And then with your calculator, if you have the ClassWiz, it's super easy to simply scroll back and delete the negative signs. And then without having to retype the whole thing over again, you can get the positive 0.5 value. And we see that that is symmetric. So again, negative 3.366 rounded. And that indicates that these other values will probably be symmetric also. So let's adjust. Again, wanting to point out with the Casio that it's easy to go back and edit what you previously input. And we can get our positive 0.1. And then remember, that's probably going to be symmetric with your negative 0.1, but I would suggest that you evaluate it just to make sure. Negative 3.973. And then one more time. Again, simply go back. This time we're going to input a 0 to do our 0.01. That's the positive. Negative 3.997. That's actually going to round to negative 4 if I go to 3 decimal places again. So I'm just going to say rounded to 3 decimal places, that would actually be negative 4. And that right there indicates what our limit is. And so that in turn is what we need to define our function as. So f of 0 would need to be defined as negative 4 so that the limit exists, the function value exists, and the limit equals the function value. Next, problem number 6. If an equation of the tangent line to the curve y equals f of x at the point a equals 4 is this equation. They want us to find f of 4 and f prime of 4. Okay, so here's one of the things that we know. The standard form of the equation of the tangent line, if you use point slope form, y minus y1 equals m x minus x1. If we use the point slope form and want the equation of the tangent line, then that's going to be x1 is whatever number you want. Say a, y1 would be the function value at a. So here you've got your x and your y coordinate depending on whatever number you choose for a. The m, remember the slope of the tangent is the derivative at that value that you've chosen, so f prime of a. So knowing this formula, we can manipulate this into slope-intercept form and then line it up with the equation we're given. So I'm going to distribute the f prime of a and bring over the negative f of a. That's going to give me f prime of a times x minus f prime of a times a plus f of a. Now, let's make a note here that here's our x, and so this must be our slope. F prime of a times a, that's a value, that's a number, and so is f of a. So this entire expression here is b, y equals mx plus b, and here we know those values from the given equation. So we can say that, first of all, every a in this situation can be replaced with 4. That's what our value is. And then we can say f prime of 4, which is the slope, is the slope of our equation, which is 4. Notice that that is one of the pieces they ask us to find. F prime of 4, that's done. And now that we know what that is, we can replace f prime of 4 with what we know. Okay, so going this way, that's going to be negative 4 times 4 plus f of 4. All of this has got to equal b, which is, in this case, negative 7. And then we have an equation here we can solve for f of 4 and get the other piece they asked for. Negative 4 times 4, negative 16 to the other side makes a plus 16. And then we can see that f of 4 is 9. And that's going to do it for this problem. Next, number 7, find the number c that satisfies the conclusion of the mean value theorem on the given interval. So here we have the function f of x equals 2 square root of x on the interval from 0 to 9. And what the mean value again says, it says that somewhere along your function on a given interval, there will be a point called c where the slope of the tangent at c is the same as the slope of the secant containing the endpoints of your interval. So the first thing we need to do here is we need to find the slope of the secant. And then we will simply find the value c that gives us the slope of the tangent to be the same value. Okay, so here we go. Finding the slope of the secant, just like we find the slope of any line, we need 2 points. And in the numerator, remember that's y2 minus y1, but y is f of x, and here we would have f of 9. That's going to be f of 9 minus f of 0, those are the endpoints of my interval, over 9 minus 0. And then we need to calculate that slope. So f of 9, plugging a 9 in, is going to give me 3 times 2, which is 6. F of 0, again, that's going to be square root of 0, which is 0. 0 times 2 is 0. All over 9 minus 0 reduces to 6 over 9, which is 2/3. So this is our target slope. This is what we want the slope of the tangent to be to satisfy the mean value theorem. Now, how do you find slope of the tangent? Well, you need the derivative. And so we're going to have to calculate f prime of x. The best way to do that in this case, since we have a radical function, is we're going to rewrite that as 2x to the 1/2 and then use the power rule. So we say the 1/2 times 2 is 1. X to the 1/2 minus 1 is negative 1/2, which is the same as 1 over x to the positive half, which is the same as 1 over square root of x. So this is our derivative. Remember, we need this to be equal to the slope of the secant. Derivative is the slope of the tangent. Again, we need the 1 over square root of x to equal 2/3. So let's solve for x. Cross multiply. We're going to get 2 square root of x equals 3, and divide by 2. Square root of x is 3 over 2, and simply square both sides. And so here we can see that our value of c, remember that's a value of x within the interval, is going to be 9/4. And it might be nice to check and make sure that that value that you get is actually between 0 and 9. And that's going to do it for that problem. Next, number 8. Find the slope of the tangent line to the following equation at the indicated point. Slope of the tangent. That means we're going to need the derivative. And here they have given me a rational function with trig functions involved. And this looks rather nasty. So what I'm going to do is I'm going to see if I can manipulate this equation into something a little easier to take the derivative of. First of all, notice the denominator is a monomial. It's one term. And so I'm going to separate this into separate fractions. 4 over secant x minus tangent x over secant x. And then I'm going to remember that secant x is 1 over cosine x. So if I replace secant x in both of these cases with 1 over cosine x, I'm going to get division with fractions, which means I'm going to need to do the KCF. We're going to keep, change, flip. And then this first fraction is going to become something really nice. That's going to just simply become 4 cosine x. Now again, tangent, I can replace tangent with sine x over cosine x. If I take and multiply by the reciprocal of 1 over cosine x, then that's going to give me cosine x over 1. Notice what happens here to my cosines. And again, that simplifies really nice to just sine of x. Now this equation is going to be much easier to take the derivative of. Here we go. Y prime is, the derivative of cosine x is negative sine x. Remember that the coefficient here just comes along for the ride. And then we need to take the derivative of negative sine x. Well, the derivative of sine x is cosine x. And here the negative just gets attached to negative cosine x. So there's our derivative. And now what we need to do is, it says we need to find the slope at this point, which means that we need to evaluate all of the x's at pi over 4. So I would say the slope of the tangent is negative 4 sine pi over 4 minus cosine pi over 4, and then plug that into our calculator. And as you can see here, I've input that in my ClassWiz. Just a reminder that this needs to be in radian mode since those angles are radian. And also notice that the ClassWiz gives us our exact answer in simplest radical form, which is freaking sweet. So our answer here, negative 5 square root of 2 over 2. And that's going to do it for this problem. Next, number 9, find the equation of the tangent line to this curve at this point. So our equation y equals 7x minus x squared at the point 2, 10. Now remember, to find the equation of the tangent, we first need to find the slope of the tangent. And that means that we're going to have to find the derivative. So y prime is, using the power rule, the derivative of 7x is 7. The derivative of x squared is 2x. There's our derivative. And then to find the slope of the tangent, we need to evaluate at our given x, which is 2. 7 minus 2 times 2 is going to give us 7 minus 4, which is 3. So there's the slope of the tangent. And now for the equation part, we're going to use the point slope form. Y minus y1 equals m x minus x1. Our y1 is 10. Our slope is 3. And our x1 is 2. And we're done. But you probably don't want to leave it in point slope form. Probably want to write that in slope intercept form. So let's go ahead and do the distributive property and bring the negative 10 over and simplify. 3 times x is 3x. 3 times negative 2, negative 6 plus 10. Negative 6 plus 10 is 4. And we're done. That is the equation of the tangent line to our function at the given point. Next, number 10, find the equation, this time of the normal line to y equals x squared minus 6x at the point 1, negative 5. This is going to work exactly like number 9, except when we find the slope of the tangent, we will then need to convert it to the slope of the normal. All right, first, slope of the tangent means that we're going to have to find the derivative. And the derivative of x squared is 2x. The derivative of negative 6x is negative 6. And then the slope of the tangent is going to be this expression, 2x minus 6, evaluated at 1 in this case. 2 times 1 minus 6. That's going to be negative 4. Now remember, this is the slope of the tangent. Now to get the slope of the normal line, we need to take this slope and flip it and change the sign. Because if you remember, the normal line is perpendicular to the tangent line. So once we get our tangent slope, we need to make it perpendicular. Perpendicular line, flip and change the sign. So there is the slope we're going to use. And then we simply go to the point slope form. Y minus, y1 minus a negative makes it a plus, equals m, slope of the normal, x minus, x1, and we're done. If you want the answer in point slope form. Probably going to want that answer in slope-intercept form. So let's distribute and move the 5 over. And we're going to get 1/4 x minus 1/4 minus 5. And then if we combine like terms, that's going to be minus 21/4. And that is the answer we're looking for right there. Number 11, use implicit differentiation to find an equation of the tangent line to the curve at the given point. So, noticing on the left-hand side, we have y times the sine of 5x. That's going to require the product rule. On the other side, x times cosine of 5y will also require the product rule. And just as a reminder, when you're doing implicit differentiation, anytime you differentiate a y variable, you have to attach a y prime. Here we go. First, the derivative of the first. The derivative of y is 1. But since it's a y, we have to attach a y prime. We have the derivative of the first times the second plus the first times the derivative of the second. And since the angle is not just x, we will have to use the chain rule. So the derivative of sine is cosine. The stuff inside stays the same, multiplied by the derivative of the angle, which is 5. On the other side, the derivative of x is 1 times the second plus the first times the derivative of the second. Again, this is going to require the chain rule. So the derivative of cosine is negative sine. The stuff inside stays the same. And then when we differentiate the angle, since it has a y, we're going to have to attach a y prime. And so that is the first step using implicit differentiation. The next step, we can go ahead and evaluate for x and y, and then simplify. All right, so that'll give us y prime times sine of 5 times x, where x is pi over 5, plus y, we have a y, that is pi over 10, times the cosine of 5 times x times 5. And then on the other side, 1 times anything is itself, so that'll be cosine of 5 times y plus x. We have an x by itself times negative sine of 5 times y times 5y prime. And then we can simplify. 5's reduce out, gives us the sine of pi. Here, 5's reduce out, gives us the cosine of pi. 5 goes into 10 2 times, giving us cosine of pi over 2. And 5 goes into 10 2 times, giving us negative sine of pi over 2. Next, if we scroll up some, we're going to simplify. Sine of pi is 0, and that will effectively eliminate that term. Plus pi over 10 times the cosine of pi. Cosine of pi is negative 1, and then don't forget we have that times 5. On the other side, we have the cosine of pi over 2, that is 0, plus we have pi over 5 times. Now, sine of pi over 2 is 1, and then that negative will make that negative 1 times 5y prime. All right, next step. 5 goes into 10 2 times, giving us negative pi over 2. On the other side, these 5's cancel, giving us negative pi times y prime. If we divide both sides by negative pi to isolate the y prime, we're going to get that that is positive half. Now that is also the slope of our tangent. And now we can use the point slope form to get the equation of the tangent line. Here we go. Y minus y1. Remember the y was pi over 10 equals m, which is a half, x minus pi over 5. And then if we simplify that equation, doing the distributive property and bringing the minus pi over 10 over, that's going to give us 1/2 x minus pi over 10 plus pi over 10. Those will effectively eliminate each other and give us y equals 1/2 x for our simplified final answer. Next, number 12, we simply need to find the indicated derivative. Here we're looking for f prime of 3, and so the first thing we need to find is f prime of x. The derivative of x cubed is 3x squared using the power rule. The derivative of e to the x is itself, since the exponent is just x, and the derivative of a constant is 0. And now we can evaluate at 3. Giving us 3 times 3 squared minus e to the third. 3 squared is 9 times 3, that's 27 minus e to the third, and that would be our exact answer. 27 minus e cubed. Next, number 13, we need to find the derivative, evaluated at a half, and we have multiple of x's. We've got x cubed times e to the 2x. That's going to require the product rule. So we're going to take the derivative of the first times the second plus the first times the derivative of the second. Now the derivative of e to the 2x is itself And since the exponent is not just x, we will have to apply the chain rule. So multiplying that times the derivative of the exponent gives us a 2. That is the derivative. Now we can evaluate that at a half. So that's going to give us 3 times 1/2 squared times e to the 2 times a half plus 1/2 cubed times e to the 2 times a half times 2. And that'll simplify. 1/2 squared is a fourth. A fourth times 3 is 3/4. E to the half of 2 is 1, and you don't really need to write the 1. Plus, over here we have half cubed. 1/2 to the third is 1/8, but an 1/8 times 2 basically will eliminate one of those factors of 2 and put that down to a fourth. E to the half of 2 is 1 again. And then notice that these are like terms. 3/4 e plus 1/4 e is 4/4 e, or just e. And so that answer is simply e. Next, number 14. We need to find the derivative evaluated at 2. The derivative of 1 over x. What we should do first is we should rewrite that as x to the negative 1 times natural log of 3x, and that'll make it a lot easier to take the derivative using the power rule. So now we can say the derivative of x to the negative 1 is negative 1 x to the negative 2 minus the derivative of natural log is 1 over x, but that's if the thing you're taking the natural log of is just x. So since this is 3x, that's going to be 1 over 3x multiplied by the derivative of the stuff inside using the chain rule. And then these 3's will reduce out. And we can now evaluate at 2. I'm going to put this back into fraction form. So that'll be 1 over x squared, but x is 2. Minus 1 over x, again x is 2, which will give us negative 1/4 minus a half, or negative 3/4. Next, number 15, we need to find the derivative and evaluate at negative 2. And the derivative of inverse tangent is 1 over 1 plus x squared. But since our angle is not just x, we're going to have to apply the chain rule. Again, the derivative of inverse tangent is 1 over 1 plus whatever the angle is squared. Here the angle is x squared, which is going to be squared. And then you do need to multiply by the derivative of the angle, which is 2x. And that will simplify to 2x over 1 plus x to the 4th. And then we can evaluate that at negative 2, giving us 2 times negative 2 divided by 1 plus negative 2 to the 4th, negative 4 over 1, that's going to be plus, a negative number to an even power becomes positive, and that's going to be 16. So our final answer in simplest form, negative 4 over 17. Negative 4 over 17, and we're done. Next, number 16. Look, we need to simply find the derivative. We don't have to evaluate this time. But I see that my function is not only a rational function, but it involves a trig function. So what I'm going to do, since I don't really like to do the quotient rule or have to take the derivative of secant, I'm going to see if I can simplify this. Here we go. I happen to know a trig identity that says that secant is the same as 1 over cosine x. And then I can apply the keep, change, flip. So that'll give me x squared over 1 multiplied by the reciprocal of this fraction, cosine x over 1, which gives me my new function to be x squared times cosine x. And then I can apply the product rule. To take the derivative, we're going to do the derivative of the first times the second plus the first times the derivative of the second. And the derivative of cosine is negative sine x. And that will simplify to 2x cosine x minus x squared sine x, and that is our final answer. Next, number 17, we need the second derivative. So to take the first derivative, notice that we have two functions in terms of x multiplied. We're going to have to use the product rule. The derivative of the first times the second plus the first times the derivative of the second. And that was pretty straightforward, but remember we need the second derivative, and so then we get to repeat the process. However, now we have two terms, and the second term is going to require the product rule again. So, for the first term, the derivative of sine is cosine. That's going to leave us just 3 cosine of x plus, and then the product rule, the derivative of the first times the second plus the first times the derivative of the second. And the derivative of cosine is negative sine x. And then if I simplify, notice that I do have like terms. So 3 cosine x plus 3 cosine x, that's going to give me 6 cosine x. And then this last term is going to be minus, we have a negative times a positive, giving us minus 3x sine x. And that is the final answer in simplest form. Next problem, number 18. We need to find the derivative of g of t. Here we notice that we do have the product of two functions in terms of t, so we're going to have to apply the product rule again. And what I'm going to do to start with is I'm going to rewrite this radical expression in terms of a rational exponent, and that'll make it a lot easier to take the derivative of that factor using the power rule. Alright, so here we go. The derivative of g of t says we're going to take the derivative of the first, 1/3 times 3 is 1, t to the 1/3 minus 1 is negative 2/3. That's the derivative of the first times the second, plus the first, 3t to the 1/3, times the derivative of the second. Now the derivative of natural log of t is just 1 over t, and since it's not just t, it's 9t, we're going to have to apply the chain rule, multiplying by the derivative of the stuff inside. And then a couple of steps of simplification are in order. Making this negative exponent positive means we're going to put it in the bottom. That's going to be 1 over t to the 2/3 times natural log of 9t plus, I'm going to put this back into radical form, 3 cube root of t, and these 9's will cancel, multiplied by 1 over t. So g prime of t, if I simplify again, we can see that this natural log of 9t, I can put it over 1 and then multiply those into a single fraction, giving us natural log of 9t all over, and if I put this back into radical form, that'll be cube root of t squared plus, notice on this second term,
I think I may have prematurely put this back into radical form. If I go ahead and rewrite that as t to the 1/3, I can see that I do have t's top and bottom, and I can reduce those. So this t has a 1 for an exponent. If I minus the 1/3 to get rid of the t in the top, that's going to give me 3 over t to the 2/3, or the cube root of t squared. And then I can see that I have a common denominator. So my final answer for g prime of t in simplest form is going to be the natural log of 9t plus 3 all over the common denominator of cube root of t squared. Next, number 19. Here we need to find the derivative. We have the inverse sine of x squared with a coefficient of 7. We know that the derivative of inverse sine is 1 over the square root of 1 minus x squared. So this coefficient is just going to hang out front. We're going to have our derivative of 1 over square root of 1 minus x squared. But here our angle is x squared, so that's going to be squared. And since it's not just x for the angle, we are going to have to use the chain rule. So we will need to multiply by the stuff inside, which is 2x. And then that will simplify. The 7 and the 2x, those are both in the numerator, giving us a numerator of 14x all over the square root of 1 minus x to the 4th. And that is the simplest form of the derivative of this function. Next, number 20. A man climbs to the top of a 6-meter ladder that is leaning against a wall. The bottom of the ladder begins to slide away from the wall at a rate of 1 meter per second. How fast is the man approaching the ground when the ladder makes a 20-degree angle with the ground? So let's sketch a picture of this end result and see what's going on. Alright, so here we have our picture with our man at the top of the ladder, and the ladder on its way down makes an angle of 20 degrees with the ground. I'm going to label this side x and this side y, representing the x coordinate, or the x axis and the y axis. And what they give us here when it says that the ladder begins to slide away from the wall at a rate of 1 meter per second, that's the rate of change of x, which is the derivative of x, or the x prime. That is 1 meter per second. We want to know how fast the man is approaching the ground. That is, how fast is this y side changing, and that is y prime. That's what we're looking for. And we have a formula that relates all 3 sides of a triangle, and we have a formula that relates all 3 sides of a right triangle, the Pythagorean theorem, and that's the equation we're going to start with. So x squared plus y squared equals, I'm going to say L squared. L represents the length of the ladder, or the hypotenuse. And then I'm going to differentiate that equation. So we have the derivative of x squared, which is 2x, times the rate of change of the x, plus the derivative of y squared times the rate of change of the y, and the derivative of L squared multiplied by the rate of change of L. And then we're going to plug in for the pieces we know. We know that x prime, the rate of change of that side, is 1, and so that will simplify to just 2x. 2y, y prime, I don't know any of those values yet. And the rate of change of the ladder. The ladder doesn't change length as it slides down the wall. It continues to be a 6-meter long ladder. So that rate of change is 0, making this entire side go to 0. And then what we can do is we can isolate the variable that we're trying to solve for and then see if we can find the remaining pieces. Okay, next, moving the 2x to the other side is going to give us 2y, y prime equals a negative 2x. And then if I divide both sides by 2y to isolate the y prime, that's going to reduce to just negative x over y. And so if I simply knew the length of the sides x and y at this point, I could find the rate of change of the y side, which is the speed at which the man is approaching the ground. So here we go. Using our trigonometric identities, we know that sine theta is, here my theta is 20, sine theta is y over r. But my r is the length of the ladder. And so then what I can do is multiply both sides by 6, and I'll know the value of y. And so we can see that y is whatever 6 sine 20 is. I'm actually going to leave that 6 sine 20 to leave it exact. Okay? We also know that cosine of theta, cosine of our angle, is x over r. Again, if I multiply both sides by 6, then I'll know what x is. Here x is 6 cosine of 20. And now that I know x and y, I can come over here and plug in. So x is 6 cosine of 20. Y is 6 sine of 20. Our 6's will cancel. We know that cosine over sine is cotangent. And so, since that's not going to be a nice number, that would actually be the exact value. But I do want to go ahead and approximate that, say, to the nearest 10th, 100th. It doesn't specify in the problem where they want us to round to, but we can approximate that value. And to do that, I'm going to use my calculator and input this cosine 20 over sine 20 and make that a negative. All right, here we go with our class whiz. In degree mode, we're going to say negative fraction. We have cosine of 20 divided by sine of 20. And rounded, that's going to be negative 2.75. And again, the units here would be meters per second. And it is negative because that length is decreasing. The man is moving in a downward direction. But his rate of change is negative 2.75 meters per second. Next, number 21. Find the critical numbers for the following equation. In order to find the critical numbers, we need to take the derivative and set it equal to 0 and solve for x. So to find y prime, given a rational function, we're going to need to use the quotient rule. We've got the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. And then we need to set that equal to 0 and solve for x. So replacing y prime with 0. Notice if I multiply both sides by the denominator, here instead of recopying all this, I'm just going to say d for denominator. If I multiply both sides by the denominator will cancel, and over here we still have 0. So really we're just concerned with where the numerator equal to 0. If I simplify the numerator, we're going to have 1 plus x squared minus 2x squared. Combining like terms is going to give us a negative x squared. And then if I move that to the other side, we're going to get x squared equals to 1. Taking the square root of both sides, we can see that our critical points are plus and minus 1. And that's it for this problem. Next, number 22, find the x-coordinates of the inflection points for the following equation on the indicated interval. And so here, inflection points occur at the second derivative, so we're going to need to find y double prime. And in order to get there, we need to start with the first derivative. Here we have sine squared x, which is going to require the power rule. So the 2 comes down, the stuff inside stays the same, the stuff inside being the sine x, and then we minus 1 from the power, would give us just sine x to the 1, or just sine x, and then multiplied by the derivative of the stuff inside, which would be sine x, the derivative of which is cosine x. There is our first derivative. And then to find the second derivative, we're going to need to use the product rule. So we've got the derivative of the first. The derivative of sine is cosine x times the second plus the first times the derivative of the second. The derivative of cosine is negative sine x. And then we need to set that second derivative equal to 0 and solve for x. Simplifying is going to give us 2 cosine squared x minus 2 sine squared x. Next, I want to divide through by 2 just to simplify this equation some. Getting rid of those coefficients of 2. That's going to give us 0 equals cosine squared x minus sine squared x. And then in the next step, if you recognize what we have here, this is one of our trig identities. This is the formula for cosine of 2 theta. So I'm going to do a substitution, replacing with cosine of 2 theta. And then what we can do is we can say, well, can we just figure out what angles in the unit circle have an x-coordinate of 0? And that'll be what our 2 theta should equal. We know that in the unit circle, the angles that have an x-coordinate of 0 are pi over 2 and 3 pi over 2. Dividing through by 2, that's going to give us pi over 2 divided by 2, which is pi over 4. 3 pi over 2 divided by 2 is 3 pi over 4. And once we get these values of x, we need to check and make sure that they are both on the interval given. Pi over 4 and 3 pi over 4 are both between 0 and pi, and so these are both values of x where we will have an inflection point. Next, number 23, determine the intervals for which the equation is concave down. That means we're going to need to find the second derivative and then find out where the second derivative is negative. Starting with the first derivative, that's going to be 6x squared minus 2x. The derivative of the constant goes to 0. Taking the second derivative is going to give us 12x minus 2. And then what we need to do is we need to know when is this negative. So next, we need to find the critical point. Setting this equal to 0, solving for x, we're going to have 12x equals to 2 divided by 12 and reduced is going to give us 1/6. And then on a number line, knowing that this is our only inflection point, we need test points. So less than 1/6, 0. Greater than 1/6 is 1. We're going to plug those test points into our second derivative to see whether we get a negative or a positive value. Plugging in 0, we get -2, which is negative. Plugging in 1, we get 10, which is positive. And this section of the number line indicates where we're going to be concave down. So we would say that this graph is concave down from -infinity up to 1/6. And that's going to do it for this problem. Next, number 24, we need to evaluate this definite integral. Now it says use substitutions may help, but in this case I can see that I have just a simple polynomial expression, so we're going to find the antiderivative of each term separately. The antiderivative of 2x is x squared. We know that because when you do the power rule backwards, you have to add 1 first to the exponent, giving us a squared, and then you divide the coefficient by the new exponent. 2 over 2 is 1. So that's how we get the antiderivative of the first term. And then for the next term, that's going to be negative. Adding 1 to 2 gives us x cubed. Dividing the coefficient by the new exponent gives us just a 1. And then this antiderivative needs to be evaluated from a half to a third. So that's going to give us 1/2 squared minus 1/2 cubed. That is this expression evaluated at a half, and then we minus the same expression evaluated at a third. That'll be 1/3 squared minus 1/3 cubed. And then to work that out, you can either do it manually or electronically. I'll show the steps. 1/2 squared is a 1/4. 1/2 cubed is an 1/8. Minus 1/3 squared is a 9th. 1/3 cubed is 1/27th. And then I'm going to pull up my class whiz for help. So we've got 1/4 minus 1/8, which is 1/8, minus 1/9 minus 1/27 is 2/27. And then subtracting these values, we have 1/8 minus 2/27, giving us a final answer of 11 over 216. And that is the answer for question 24. Next, 25, another definite integral, starting with the antiderivative of e to the x, which is e to the x, minus the antiderivative of 1 over x. And if you think backward, what would I take the derivative of to get 1 over x? That is natural log of x. So the antiderivative of 1 over x is natural log of x. There's my antiderivative. This expression needs to be evaluated from 2 to 1. So we're going to get e squared minus natural log of 2. That is this expression evaluated at 2. And then we're going to subtract the same expression evaluated at 1. E to the 1 is just e, minus natural log of 1. And then if I simplify, e squared minus natural log of 2 are going to stay the same in order to keep the answer exact, minus e, and then we know that the natural log of 1 is 0. So that just goes to 0. And then this would be our answer if you want the exact value. Otherwise, you would need to put that into the calculator if they ask for an approximate value. And one quick note, you could also express this in this form. If you want to rearrange the terms, that's fine. Both of these answers are numerically equivalent, and so both would be given full credit. Next, number 26, we have another definite integral. What I want to do first is I want to rewrite this integral in a different format. Notice that the numerator is 6. What I can do is I can pull that to the front as the coefficient of 1 over the square root of 1 minus x squared. And then since this is now a coefficient of this fraction, what I can do is I can actually pull that in front of the integral. So that's going to give me 6 times the integral from 0 to a half. And then this you should recognize as one of our derivatives. It is the derivative of inverse sine of x. And so what I can do, doing the antiderivative, would give me the inverse sine of x. So let's rewrite like this. This is 1 over square root of 1 minus x squared with respect to x. Forgot my dx there. And then we know that the antiderivative of this fraction is inverse sine of x. And that needs to be evaluated from 0 to a half. So we're going to have 6 times the inverse sine of a half minus the inverse sine of 0. So what is the inverse sine of a half? Well, that basically says where is y a half in the unit circle? Somewhere from negative pi over 2 to pi over 2, that's going to produce an angle of pi over 6. And then the inverse sine of 0 is 0. That's where y is 0. Add an angle of 0. And then this is going to simplify nicely. The 0 disappears. The 6 is reduced. Our answer is pi. And that's going to do it for problem 26. Next, 27, we have another definite integral. And this time I am noticing that I've got the square root of 1 minus x squared, and that is multiplied by x. So this is one of those cases where it's probably going to be to our advantage to use a u substitution. Let's say let u equal the radicand. 1 minus x squared, the stuff under the radical, and then I immediately differentiate both sides, giving me du equals the derivative of 1 minus x squared is minus 2x times dx, dividing both sides by negative 2x, is going to tell me what I can replace dx with. So, simplifying, that's going to give us the integral from 0 to 1. The x is still here, but 1 minus x squared is u. So we're going to replace that with u. And then we're going to replace dx with what it's equal to, which is du over negative 2x. And now we can see that this substitution is going to work well because these x's will reduce out, leaving me an expression completely in terms of u. So we're going to have the integral from 0 to 1. Don't forget about this negative 2 in the denominator. That's the same as 1 over negative 2 times the square root of u du. And then since this is a coefficient, we can bring him to the front, giving us negative 1/2 the integral from 0 to 1. And now I'm going to rewrite the radical symbol as a rational power. That's going to make it easier to integrate. So taking the antiderivative, that's going to give us negative 1/2. If I add 1 to the power, that'll give us u to the 3/2. And then I need to divide by the new exponent, which is the same as multiplying by the reciprocal. That is our antiderivative, which we can then replace u with what it's equal to, which is 1 minus x squared. Okay, so then this is going to equal, here these 2's reduce out, giving us negative 1/3, 1 minus x squared, to the 3/2, and then remember this needs to be evaluated from 1 to 0. Okay, so plugging in 1 first, we're going to have negative 1/3 times 1 minus 1 squared, all of that to the 3/2 power, and then minus a negative will make that a positive 1/3. 1 minus 0 squared to the 3/2 power, which will simplify. 1 minus 1, this becomes 0. And 0 to any power is still 0, and 0 times anything is 0. That's just 0. Plus 1 minus 0 is 1. 1 to any power is 1, and then 1 times 1/3 is 1/3, giving us a final answer of 1/3. Next, number 28, we have another definite integral, and this time this fraction looks like something we've seen before. In fact, it is the derivative of the inverse tangent of x. So we know the antiderivative of 1 over 1 plus x squared will be the inverse tangent of x. So what we're going to have the inverse tangent of x evaluated from square root of 3 to 0. So that's going to give us the inverse tangent of the square root of 3 minus the inverse tangent of 0. And the inverse tangent of square root of 3, pi over 3. Minus the inverse tangent of 0 is 0. And that's going to give us a final answer of pi over 3. And that's going to do it for this particular problem. Next, number 29. Here we have another definite integral where we have 3x times e to the x squared. Notice the difference in degree of the exponent of the e and the coefficient here is a difference of degree 1. And that is a good indication that we want to do a u substitution. So we're going to say let u equal the higher degree of x. We're going to let u equal x squared. And then if we differentiate both sides, we're going to get du equals 2x dx. Dividing both sides by 2x is going to give us the expression that we can substitute for dx. Now, rewriting the integral. From 0 to 2, this 3x is still here, but now this becomes e to the u because we let x squared be u, and dx is going to get replaced with du over 2x. And then here we can see that this is going to work nicely because we have an x top and bottom, and those x's will reduce out. Now, we do have a 3 over 2, so that's going to give us the integral from 0 to 2 of 3/2 as the coefficient of e to the u du, and then that 3/2 can be pulled out to the front. Next, simplifying this integral, I'm going to pull out the 3/2. I'm going to take the antiderivative of e to the u, which is e to the u, and then I'm immediately going to replace u with what it's equal to. Remember, we let u be x squared. So that's going to be 3/2 e to the x squared evaluated from 2 to 0. And that's going to give us 3/2 e to the 2 squared minus 3/2 e to the 0 squared. Simplifying is going to give us 3/2 e to the 4th minus 3/2. Now this right here, 0 squared is 0, and e to the 0 is 1. So 1 times 3/2 is just 3/2. This answer would be fine. If you want to factor out the 3/2, you can, but it's not required. And that would give us 3/2 e to the 4th minus 1 Either one of these answers would be sufficient. Next, number 30, they want us to find the area under the curve. That indicates a definite integral for this equation on the given interval from 0 to pi over 3. So we're going to rewrite this as a definite integral from 0 to pi over 3. We want the antiderivative of secant squared x tangent squared x with respect to x. And this one is a little tricky as far as picking the appropriate u substitution to make this a lot easier to find the antiderivative of. What we want to think is, what would you take the derivative of to get secant squared x? And that is tangent. So we're going to say let u equal tangent x. And then if I differentiate both sides, the derivative of tangent is secant squared x dx, dividing both sides by secant squared x is going to tell us what we need to replace dx with. Now, notice that we did say to let u be just tangent of x. Over here we have tangent squared x. So if I do my u substitution, that's going to become simply u squared. So here we go, rewriting this integral from 0 to pi over 3. We're going to have our secant squared x times u squared, and then dx gets replaced with du over secant squared x. Notice that that will eliminate the secant squared x's, giving me an integral in terms of u only. Now, rewriting the integral from 0 to pi over 3, this is simply u squared du. The antiderivative of u squared, if we add 1, gives us a u cubed, and then divide the coefficient by the new exponent, giving us a third. And then we can replace u with what it's equal to. And u was just tangent x. So this is going to be tangent cubed x, and then evaluated from 0 to pi over 3. That's going to give us 1/3 tangent of pi over 3. I'm going to write it like this: quantity cubed minus 1/3 tangent of 0 quantity cubed. And then we can simplify this expression using the Casio. What I want to know is, what is tangent of pi over 3 cubed? Well, tangent of pi over 3 is square root of 3, and then that answer cubed gives me 3 square root of 3. So that's going to be 1/3 times 3 square root of 3 minus, and then I believe the tangent of 0 is 0, which makes this entire term go to 0, so I don't really have anything to subtract. That's just 1/3 3 square root of 3. Oh, and then these 3's cancel. Look at that, how nice that simplifies to just square root of 3. Next, 31, the acceleration of a function and the initial velocity are given for a particle moving along a line. Find the velocity at time t and the distance traveled during the given interval. So if I have the acceleration equation, we know that the antiderivative will give us the velocity. So capital A of t, remember we use a capital letter to represent an antiderivative, that will equal our velocity function, and we need to do the antiderivative of t plus 4. So for the t term, we're going to add 1 to the power, and then divide the coefficient by the new exponent, 1/2 t squared, plus the constant just gets a t, And then we need a plus c, because this is a general antiderivative. We need to allow for any constant that may have been there. And now we're going to find out what that constant is based on this given initial condition. We know that when t is 0, the velocity is 6. So now the velocity is 6 whenever t is 0. So 1/2 0 squared plus 4 times 0 plus c. These both go to 0, telling me that c is 6. And then we can come back to here and say that our velocity equation at time t, that means the general velocity equation is 1/2 t squared plus 4t plus 6. That is the answer to the first part of the question. And then to find the distance traveled, we need the antiderivative of velocity. So capital V, the antiderivative of velocity, will give me the distance or position equation, call it s of t, and then we need to do an antiderivative again. So adding 1 to the first exponent gives me t to the third, and then if I divide 1/2 by 3, I get a 6th, plus adding 1 to the next exponent. 1 plus 1 is 2. Dividing 4 by 2 gives me a 2. The 6 is going to get a t, and we don't need the plus t since this time we're doing a definite integral from 0 to 10. So the distance traveled would be the integral from 0 to 10 of the velocity equation with respect to t, which we now have the antiderivative, would be 1/6 t cubed plus 2t squared plus 6t, all of that evaluated from 0 to 10. Now, the nice thing about doing this evaluation is when I plug in the 0, since everybody has a t, that is just going to go to 0. So really all I need to calculate is this expression evaluated at 10. So that's going to give us 1/6 times 10 cubed plus 2 times 10 squared plus 6 times 10. And then if we evaluate that using our Casio, we're going to get 1280 over 3, which is approximately 426.7 rounded. So if they want the exact answer, that would be 1280 over 3, or approximately 426.7, whatever the instructions ask for. And if I go back to our instructions, it doesn't specify. And if it doesn't specify, usually they want the exact value. Notice that our distance was measured in meters. So if we want to include the appropriate units, we would say meters or meters. And that's going to do it for that problem. Next, number 32, the rate in gallons per hour at which oil leaks out of an oil tanker truck that crashed is represented by the function. And so here we have the function that represents the rate at which we're losing oil. How much oil leaks out in the second and the fourth hours of the leak? So the second hour would be represented by from the end of the first to the second. In other words, if you're finding how much oil leaked out given the rate, that's going to be the integral from A to B of the rate with respect to t. So in the second hour, that's going to be from 1 to 2. Does that make sense? From 0 to 1 would have been how much oil we lose in the first hour. And then from 1 to 2 would be how much oil we lose in the second hour. So we're going to want to do this integral, and we're also going to want to do the integral from 3 to 4. That's going to take care of the fourth hour. And so we need to set up these integrals separately and evaluate. So here I've got my first integral set up. We need to find the antiderivative, starting with the 1000. That constant simply gets a t, and then the antiderivative of 60t, we're going to add 1 to the power, giving us t squared. 60 divided by 2 gives us a 30. And then we need to evaluate this from 2 to 1. Plugging in the 2 first is going to give us 1000 times 2 minus 30 times 2 squared. Okay, that minus 1000 times 1 minus 30 times 1 squared. And giving us 2000 minus 2 squared is 4. 4 times 30 is 120 minus, this is 1000 minus 30. And then I would recommend that you do the calculator from here on out. We're going to have 2000 minus 120 minus parentheses 1000 minus 30, and our final answer is 910. 910 what? Gallons of oil. And then we need to repeat the process for the second part of the problem, the integral from 3 to 4. Now this is going to be exactly the same as the previous problem except for our boundaries. Going from 3 to 4, we still have the same antiderivative. Now we're going to evaluate at 4 first. That's going to give us 1000 times 4 minus 30 times 4 squared minus 1000 times 3 minus 30 times 3 squared. And then if you want to put all that in the calculator at one time, you can, or you can do it in a couple of steps. So just showing a couple of steps here. 4 times 1000 is 4000. 4 squared is 16. 16 times 30 is 480 minus, this is going to be 3000 minus 3 squared is 9. 9 times 30 is 270. And I think then I'll grab the calculator. 4000 minus 480 minus parentheses 3000 minus 270 gives us an answer of 790. 790 what? Gallons of oil that we lose in the fourth hour. And the last problem on the practice final exam for Cal 1. It says find the maximum vertical distance between this curve and this curve on the interval from 0 to 2 pi. And so the first thing I'm going to do over here on the graph they've given me is I'm going to mark off from 0 to 2 pi. That means I could ignore all of this graph over here and then anything that shows up over here. I'm only looking for the maximum vertical distance within these range of values. Now, if you think about it, what we're really asking for is, if I look at just a couple of points here, making sure that this is going to be vertical, we're looking at the difference from this y value to this y. Okay, so let's simplify it. We're looking for y2 minus y1. That is the vertical distance between the two graphs. We need to identify which of these equations represents the top graph and which one is the bottom. Okay, so how do we do that? Well, notice that these graphs have a different y-intercept. So if I plug in a 0 for the second equation, the cosine of 0 is 1. 1 plus 1 is 2. And that gives us a point on the top graph. So then what I'm going to do is I'm going to put a box around this guy and say that he's the one on top. And then that makes this one the one on bottom, which in my equation now, this is y2, and this one is y1, because you want to subtract the larger y from the smaller y. Okay, so we can rewrite this expression then, and we can say that the distance between the two graphs, the vertical distance, is y2, which is 1 plus cosine of x, minus y1, which is negative 1 plus sine of x. So this is our equation that represents the distance between the graphs, the vertical distance, for any value of x. And then let's simplify that and write it in function notation, okay? So the difference with respect to x, negative and a negative make a positive. See, I'm going to need to distribute this negative. 1 plus 1 is 2 plus cosine x, and then distribute the negative makes that a minus sine of x. And then how do we find a maximum or a minimum? Well, we find critical points. So we need to differentiate this function, set it equal to 0 and solve for x, and then look for any solutions that are on this interval from 0 to 2 pi. Here we go. The derivative of our distance equation. The derivative of a constant goes to 0. The derivative of cosine is negative sine x, and the derivative of sine is cosine. And since that already has a minus in front, it's just going to be minus cosine x. So there's our derivative, and then we need to set that equal to 0 and solve. So 0 equals, if I factor out the negative, that's going to give me sine x plus cosine x. And then if I divide both sides by negative 1, I can just eliminate the negative sign. Okay? So then the next step that I'm going to do is I'm going to move one of these trig functions to the other side. Let's move cosine over, okay? So then the sine of x will be positive. It's going to equal to negative cosine x. And then the next step I'm going to do may seem a little weird, but it's going to make sense to me. I'm going to divide by cosine x, okay? So why do I do that? Well, for one thing, it gets rid of this trig function on the right-hand side and makes that effectively negative 1. On the other side, this will simplify to a single trig function. I know that sine over cosine is tangent. So now what I'm really trying to solve is, when is tangent of x equal to negative 1? Well, on the interval from 0 to 2 pi, the angles for tangent that produce negative 1 are 3 pi over 4 and 7 pi over 4. So these are my two candidates for where the maximum might occur at. And then if you remember, we also need to check the endpoints to make sure that the endpoints don't actually contain the maximum value. So let's do this. Let's erase this. Let's make a note that our critical points are 3 pi over 4 and 7 pi over 4. And then what we want to do is we want to set up a table that will allow us to compare all of the values of x where the maximum might occur. So here we're going to have x and our distance equation. So we need to check the endpoints, which are 0 and 2 pi, but we also need to check our critical points, 3 pi over 4 and 7 pi over 4. And then what we want to do is we want to evaluate our distance function, the original distance equation that we wrote, which was, again, d of x equals 2 plus cosine x minus sine of x. We need to evaluate this equation at these values of x to see which produces the largest value. Okay, so on my Casio, evaluating the first value of x, the first endpoint, make sure you're in radian mode, by the way. That's going to give us a distance of 3. So if I go up to my graph, what that tells me is that the distance between the y-intercepts is a distance of 3. And that's pretty easy to see because we're going from -1 up to 2. That is the distance for that value. And then with the Casio, you can simply scroll back through and delete the 0 and input your next value that you want to check. So 3 pi over 4, we're going to check that first critical point. And that's going to give us, on the Casio, 2 minus square root of 2. I would really like to have that as a decimal. So I'm going to hit the SD button. And that is 0.59 rounded. 0.59. I think what that's going to end up being at 3 pi over 4, which is, let's see, if this is pi, that would be a half, and this would be a fourth. You know what that's going to represent? That's our minimum. That's where the minimum distance occurs. Let's keep checking. Again, scrolling back through, now we're going to change our 3 pi over 4 to 7 pi over 4. And that's going to give us 2 plus square root of 2, which is approximately 3.41 rounded. And notice that that value is bigger than 3. So that means that 0 cannot be the maximum. Remember, we think this is the minimum. It seems to be the smallest so far. And then we need to check our last endpoint to see if that is bigger than 3.41. And the value we get at this endpoint is 3, which is not bigger. But that also shouldn't be any surprise since the period for these waves is 2 pi. We're going to get the same distance at 2 pi as we have at 0. Again, that shouldn't have been a surprise that that coincided with the same distance at 0. And so the final answer for this problem, the maximum distance occurs when x is 7 pi over 4, but they asked for find the maximum vertical distance. They actually wanted us to find the actual distance, and that's going to be this value here. So the answer that you would give for this problem is 3.41. That is going to be our maximum vertical distance between the two graphs. And that's going to do it for the end of the review for Calculus 1 Final Exam. So if you have any questions or comments, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.